Hello and welcome to episode 5 of the ML4Patents webinar series. We're going to do a little bit of housekeeping like we normally do, talk you through some of the features of the webinar software that you're using. As you heard just now, everyone has been muted on entry to the call. If you have any problems, please use the question field on the side of your screen in your control panel. We'll try to help you with any technical difficulties or questions you have. Speaking of questions, we'd like to encourage you to ask our presenters any questions you have throughout the course of the webinar. Don't hold your questions until the end. Go ahead and ask them while you're thinking of them. Again, there's a questions box in the control panel. Go ahead and put them there. I'll be looking at those as we go along. As I see questions that I think make sense to be answered right away during the context of the presentation, I'll go ahead and stop the guys and let them know that we have something that somebody would like to get addressed. And feel free to use this throughout the webinar. There'll be time at the end. Lastly, you'll receive an email tomorrow with a link to the recording of this webinar. And please don't forget, there's a handout section in the control panel as well. There are 2 handouts in there today, the slides that you'll be seeing throughout the course of today's webinar, as well as some material that talks a little bit about the IP Rally system. And with that, again, hello and welcome to episode 5, this time featuring IP Rally. My name is Tony Trippi. I'm founder of ML4Patents.com and managing director of Patent Informatics. And I'm joined today by Sakari Arvela and Sebastian Borquist from IP Rally. And with that, I will hand it over to Akari.
Thank you, Tony. Very nice to be here, and thank you for hosting this series. The previous episodes have been really great, and I really feel that there is demand for this kind of forum for talking about machine learning and patents and what there are. So we are IP Rally. We come from Finland, and we are one of the newcomers in this field, or I don't know if you can call us newcomers. We've been there already for 3.5 years officially, but the beginning was we were pretty much in the development mode, and the product has been out now for 2.5 years, and we are happy to explain today what we do. I believe we have a pretty insightful approach and can bring quite a new some food for thought for even long-term professionals in the field. And yeah, let's see what it will be. A few words about myself first. I'm Sakari, as Tony mentioned. I've been working in the IP field since 2004. I started to work as a patent attorney back then, and before that I studied physics. And while working as a patent attorney, I realized that there is a certain pattern that repeats when I draft patent applications and when I analyze patents. And I started to think that is there something that could be repeated here in a computer understandable format, and can you use that repeating pattern somehow to build a more efficient patent search? And quite a lot of what you see today stems from those times, but luckily quite a lot also stems from the team, the IP Rally team. We're now 24 people nowadays, and I'm happy to have my colleague Sebastian here with me today. Sebastian has been there almost from the start and knows very well what we are doing. So welcome, Sebastian, too.
Yes, thanks, Sakari. Great to be here. And a bit about my background. So I have a degree in mathematics, and I worked for many years before joining IP Rally in the software development industry. And when I first talked with Sakari and Juho, the other co-founder, this felt like an opportunity that I had to join, because this is such a hard problem to solve, the patent searching, and it felt like a perfect match for my background with mathematics and software development, and starting to develop the machine learning algorithms, which I didn't have a possibility to do in my previous work. So and like I say, I haven't regretted it 1 minute to joining this journey with IP Rally.
Yeah, the more you dig into the patent data and the deepness of the problem that we're solving, the more you fell in love with it, At least that happened to me.
Absolutely.
Yeah. Good. Okay, so a few words about what we do. IP Rally as a company, it's a patent search tool platform, fully featured platform. Basically started with prior art searching. Now we have done some FTO angles also. And the whole idea is that we kind of build it from the ground up from a little bit different angle that we will explain to you. So bringing a little bit of like patent professional thinking for the AI. So not just taking some university algorithm or ML model and starting to apply it for patent text, but really thinking that what's the problem that we are solving, and then picking the best algorithms and AI models to solve that particular problem. And one of the key ideas from the beginning has been to build a little bit something more transparent and explainable, and which somehow bridges the gap between Boolean and the current AI scene. But actually, the AI team is thinking a little bit further. So, like, how can we build a machine that understands technology very well, not just the language, but really getting into the core problem, that what is technology and how do you harness the machine to process that. I mentioned this explainability gap, and what I mean there is that, as probably many of you online know, that with Boolean searching, you kind of have the full control for your searches. You have full explainability. You exactly know why a particular hit is appearing in the results. But you need to build your queries like yourself. There's no built-in intelligence in Boolean sub-searching. Whereas the traditional AI methods, they are more like black boxes. You don't have much control. You put something in, you get something out, but that's it. And it's hard to explain why a particular hit is appearing in the results and what the machine actually does. Although there is maybe some good level of intelligence built into that, but like the lack of explainability somehow restricts its use, or at least building the trust to the tool. And this is something that we actually are solving with this method that we call Graph AI. And that brings the searcher a good level of control to the searching. It is somehow explainable. At least today we try to explain it. I hope someone also understands it. And then there is, in addition to some semantic intelligence, there is also like a next level technical intelligence built into the system, and it's also quite visual, and it's nice to explain. And we'll also talk about some of the benefits that these graphs bring, like intelligent AI-based highlighting, which is a super hard problem, but these graphs like bring us the tools to manage that problem also. One of the like everyone has these little moments in their life that like remain, and one of those was when I was involved in oral proceedings before the EPO back in like 15 years ago. And the chairman said that after the parties have been debating quite a lot about some semantic nuances, that he cut the discussion and said that after all, it's not about semantics, it's about technology. And then he like did a decision that was like rational and technically relevant. And that somehow stick to my head, and since that I've been thinking that how can we make the machine understand technology better.
Let me comment on that for just a second. You know, it's funny that particular quote was up there, because it's fascinating. 30 years ago, when people just started working with unsupervised clustering methods and just started to incorporate various machine learning methods into working with patent data, this was the #1 item that people brought up, that because of the ambiguity in the language, especially a patent corpus, there was no possible way that a machine was going to be able to understand this context or that meaning. And my response at the time was, you'd be surprised at, yeah, if you were talking about a single word out of context, sure, probably there'd be a bigger issue, but that's not generally what you're working with. You're talking about phrases, you're talking about words in context. We've heard about all of these new vectors that are being created that have much more context built into them. And so the idea that even in this context, it's not about the semantics. We got to stop focusing so much on this word is there or this word. That's a very Boolean concept. Either the word is there or the word is not. And now it's really much more about the phrase, the technology, the concept more than it is the word. So I just think that's interesting. It's fascinating to me that coming from a totally different perspective and a totally different problem, it's still the same issue, that words fail us.
Yeah, of course, the meaning of words it's super important, but that's not all, because it's the purpose of the words is to describe something, and that something is like technology. That's what patents are all about, and somehow going beyond just words and semantics, and it's what we're aiming at. And that is because technology is all about like interactions and relationships, and not just words. So every machine is more than the sum of its parts, and so on. And also the fact that the patent system was developed like a million years ago, and back then the only thing you had is that you had words, and I play sometimes with the idea that if the patent system was developed today, what would it like? Would we still write 10-page descriptions and claims with natural language, or would it be something else? Would we design it from the machine perspective so that the evaluation would also be easier? And something like that we have been like developing, like a machine understandable patent system. Sebastian can tell a little bit about how the AI came to this picture then.
Well, yeah, this is again the important thing about the semantics and technology, is that we obviously want to get away from the single words and the specific words that are used, and understand the content of the actual technological content, because of course the invention is not what's written on paper, it's some more abstract concept. And this is where the AI that we use, the graph AI, and then we get later in with how it is trained, how we can understand these connections in words that are the same thing can be described in many different ways, and how we can get to understanding that. And what we're trying to do is go kind of beyond the out of the box AI models. Of course, I mean, in theory, with AI machine learning, the ideal is that you would just have this one general model, for instance, a neural network, and it can learn anything. But in practice, obviously, we already use now for different types of data, we use different types of networks. For images, there are convolutional neural networks, and for text, we have RNNs or transformers and so on. So our idea is to build in some kind of more suitable model for this understanding of patents and technology, and this is the graph AI we use, and we will get into more details soon.
And one of the ideas was also to build something that is like expressive enough for ourselves, so that we can continue improving. We can detect where the bottlenecks are, and then take the next step and keep improving all the time. So let's have an example what the graph AI actually means. And on the right-hand side, you can see a snow thrower. There are handy devices here in Finland when you get a lot of snow in the good winters. And on the right-hand side, you see how a patent drawing specialist puts that on paper. And on the top left side, you see how a patent attorney writes a claim for an invention related to snow throwers. And on the bottom left corner, you see a graph. that is our knowledge graph that we have built. Our engine can build automatically based on this claim. And there is this saying that the image is worth 1,000 words. And that's true for the human. You can very quickly see from the image on the right that what's in there. And somehow we are building that concept, like that the graph is for the machine is more than the words that are contained in it, because it is actually makes the information like relational, and you see that the handle device appears like a few times in the claim, but how it connects to the other features of the device or other elements of the device, they are all expressed in the graph in a pretty nice way. It's like for a human eye, it's pretty informational, but also for the machine, it's really useful because the information is somehow connected. And it's proven to be really expressive model for the AI. So we basically pick all the basic elements in a mechanical case like this. We pick the motor, the handle device, the auger housing, and put them in the logical order here. But we also identify the more complex relationships, like the purpose of the frame is to connect the handle device and the auger housing. It's expressed in a logical position here, and it kind of maximizes the information then that the neural network has when it starts to process the information. And the benefits of this is that we actually get to the core problem or the basic problem of patent searching, that what is a good prior art reference. So if we use a graph as an input, like a man-powered vehicle having 2 wheels and saddle and the chain connects the pedals and real wheel, you immediately see that, okay, it starts to look like a bicycle. And of course, we expect to have some bicycles in the results when we search for this kind of technology. But if you put that input to IP Rally, you get these bicycles, but you also get the explanation that why is this hit, why was it relevant, and the AI can highlight those passages that like brought the signal and made it a relevant document, and that's of course very helpful for the human when doing the analysis part. But the normal bicycle is just one possible scenario here. Also a tricycle satisfies these criteria. It also has 2 wheels. It has a third wheel, but still it has 2 wheels. It has a rear wheel, it has a front wheel, and you get that hit too, which is of course good. And you also get the explanation that why was this hit good. And but we can go beyond that. One of the hits that you get with this graph is a snow cycle. And okay, is there a front wheel and a rear wheel? Yes, actually there is. There are many wheels here. One of them is more front than the other. There is a front wheel and a rear wheel, and they are attached to the body. So also that pops up, and it's a really good hit if you search for a novelty destroying prior art for this kind of claim or graph, then this should pop up. And this is something that as a patent attorney fascinated me, that how to build a machine that like mimics the patent examiner, that balloons the concept and finds the novelty destroying prior art. And that's what IP Rally has also been trained for. What intrigued me myself when we got into this problem that patent attorneys usually speak about like a genus, species, and something's part of something. But when we go to the linguistics, there are specific terms for them, like hyponymity. Bus is a vehicle, car is a vehicle, bus is a car. And you can build this concept in a graph like this. And when you search prior art for a vehicle or a car, then actually a bus and a car, they are both perfect prior art. They are novelty destroying documents or references. But when you search prior art for the bus, then actually a bus is better prior art, because a normal car is not a bus, but a bus is a bus. And but then on the other hand, for example, also elevator can have a car. It's a completely different meaning. And also elevator can have a bus. It's a communication bus. And somehow the machine needs to pick these small things from the input that you're giving. And we have built in this. It's not shown in the graph, but there is this information about whether it's a hyponym or meronym, as we talk in the linguistics in the graphs, and that of course may help the AI then to end up with better results. So it's a fascinating problem because there are semantics and linguistics and technology entangled to each other, and many aspects to it. Then how we have trained our AI is also interesting. First, we use this graphs because graphs that are built based on claims, because there is quite a lot of engineer thinking put into those, and they somehow tell that how an individual person could define some particular technology in words. And we just remove the patent jargon and build this graph, so it's more one-to-one to the actual technology. And then we harness the historical patent data to there is a lot of knowledge in the historical patent data because so much work has been done to find good references for patents, and we use supervised AI to capture that. Sebastian may want to say.
Yes. So in the gist of it is that we try to make our search mimic what the patent examiners have done, because we use their citations to train our model. So we try to do what they do, but obviously much quicker. And here, good thing to point out is that, as Sakari mentioned, that we do not only parse the claims into these graphs, but also the full specifications. We have all of them. Now about 80 million have been processed in this form, so we have the same structure for them also, and those are then used to train the search model, and then they are also used when the search is done. Then we have the graphs and vectors for them, and they are used to produce the results that are then shown to the user.
Yeah. So if I'm understanding correctly, based on what you guys have said, then in the parlance of what we've heard about with other machine learning related methods, there's always a vector. We've heard about doc2vec, word2vec. I mean, there's always a vector. In order to make any sort of a comparison, regardless of what other method is used going forward, there's always a vector. And so it seems to me that from what you're saying here is the vector in this case is these graphs. So the graphs are somehow translated into a vector that can then be used as a training. And by using the examiner citations, you're basically saying, well, okay, this document that was cited, we have a graph for it, and therefore a vector for it. And this other document that we think we're comparing it to, it's got a graph. And so that's where the actual point of comparison is being made between the associated graphs from a document of interest, for instance, and then the corresponding examiner X citations, for instance, that ended up being called into the novelty questioning for that document that you're referring to.
Yes, that's pretty exactly how it goes. So the graphs, obviously, to create vectors from the graphs, we need to somehow know which graphs are related to each other. Obviously, the graph is related to itself, but that's not a very interesting comparison. And here the problem again comes that probably you might use completely different terminology in the claim and the cited document. So we need to somehow then understand that these are still mean about the same thing. The invention specified in the claim is contained in this full specification, and that's what the idea of the neural network model is, to learn these connections. So okay, we have these two graphs, and this is cited from here, so the vector should probably be quite close to each other. So we then find the reference if we search with this claim, and that's how the vectors are then created. So the citations are then found when we search for them.
Okay, let me ask you, we've gotten 3 questions that have come through just a moment ago that are very similar in nature. The example that you're using so far, both of the examples that you've used so far, have been device or apparatus claims. And so I think that the big question that people are asking at this point is, what about composition of matter or method/process type claims? How are those other non-device related graphs generated?
Actually, like chemical structures, they fit very well into this graph model. And I can show also, if you have time, an example how a typical chemical claim converts into the graph. Of course, sometimes chemical language is still like very complex, and the graphs may not be optimal, but one of the nice things is that you can also edit those graphs manually. You can correct where the machine does wrong. The human can kick in and do the corrections. And then, of course, that increases the possibility of the machine to get the concept. And methods also convert to the graphs. Then we have just a little bit different logic. The method preamble comes as the root feature, and then the method steps become as the sub features of the preamble. So they work too.
Excellent.
Basically.
Well, great. Let's continue to go on. I think that addresses those questions. We'll see an example of it a little bit later.
Yep. We'll spare a good amount of time to the demo. So basically, I think we covered this aspect already, and move to the next one. So basically, as a summary, an efficient patent search is not just the results. You need to understand the search circuit. I think the graphs help in that, because they're pretty visual, and at least you know how the machine perceives the target well. Then you get a good short list of relevant results, but you can also control that. So you can modify the graph, you can give relevance feedback saying that these hits are good, and then the AI can use that information to improve the results. And then this highlighting is very helpful, because it helps in the analysis and decision making, and also they can be put part of the reports, and also the query graph is good for documentation purposes. So we feel that throughout the process, this graph may help to make the process more efficient. But I think much will become much clearer when we jump into the demo in like 10 minutes and show how it actually works. Okay, I think this is a machine learning forum, so metrics is pretty important, and knowing that we are doing the right things, and Sebastian can tell a little bit about that, and we'll also cover the qubit dataset that has been covered in the previous episodes too. So.
Yeah, thanks, Sakke. So obviously a search is only as good as its results. It doesn't matter how fancy technology we use if it doesn't actually produce something useful. So we have different ways of measuring to know how are we doing the right things, do we get the correct results. The first simple one that we check is this so-called what we call trivial sample recall. So if you search with the claim optimally, it should return the document itself, obviously, because that's kind of the best hit you can imagine for a document is itself. So this is something that's not necessarily completely trivial in machine learning cases. So it's something we use as kind of a let's say a first check that, hey, does this seem sensible? Does this at least work? If it doesn't, then we know that we have to go back to the drawing board. But if it does, then that's okay. Then at least that part is working okay. And the thing here is to note that it's not completely certain that why it might not return itself is that obviously the claim is pretty short compared to its full specification, and since we're searching from the full specifications, the documents are actually somewhat different. So that's why this is something we measure. But obviously the main thing is do you find the actual prior art, the relevant prior art, the novelty destroying documents. So what we use is we train on the patent examiner citations, and then we also use these citations, obviously then another left out set we use to check that how often do we find these citations, because that's basically what we're trying to mimic and what the user wants to find when searching. And the good part of this is that there's obviously a large amount of data available, since this is public available and there are millions and millions of citations. But the problem here is that the quality is somewhat limited in the sense that obviously an examiner cite a document that he or she has seen, and it's quite certain that the examiner has not seen all the documents that might be relevant that could have been cited. So if a document is found by our search engine and has not been cited, it doesn't mean that it necessarily is a bad document. It might have been cited if the examiner would have seen the document, but they necessarily have not. So this is an incomplete metric in that sense. It's basically impossible to get this to have a gold standard set for these searches, because the amount of documents is so vast that no human can basically go through them. And then another thing we can use is have some classification data sets, which is this qubit data set, which we'll get into more detail soon. This is obviously not exactly what we're trying to do. We're working on a prior art search engine, but at least it measures how our model understands technology in general. If it's able to do classification well, then it has understand technology on a general level. And then we are also thinking about new other types of metrics that can be used. And this is especially more important as the models go better and better, because then the existing examiner citations, the limitations of them start coming through because of the issues mentioned earlier. So we have some possible metrics that can be used that we call expert to say citation ranking. I will also get into that soon. So yes, I think we can move forward. So this is.
Let me ask you a couple of questions. We've had 2 questions come in. One I think can be addressed really quickly, and the second one I think is very relevant to everything you've been talking about here. The first question is what sources are available? Is IP Rally strictly a patent engine? Are there any opportunities for either non-patent literature or maybe corporate documents or other data to be added or analyzed by the system, or is it strictly the patent corpus that you folks have available through your system?
Currently, IP Rally covers only patent documents, but certainly it's on the roadmap to extend to NPL, starting from scientific literature standards. We'll see that. Now we are taking the first steps to make this graph conversion algorithm like better suitable for non-patent data. Clearly the road.
Outstanding. And this is a question that I had also. So I think that the person asking it put it together very nicely. When searching, do you search claim by claim with separate graphs for each claim, or do you search using the narrowest claim and of a claim tree branch, or the broadest independent claim at the trunk of the claim tree. So it's also interesting to me with regards to families. So if you've got a extended family or a simple family or some other sort of family, you've got all these independent claims, for instance, can you share just a tiny bit about at which level or how much? You mentioned earlier that you were also doing graphs for the full text, but you know, so are there graphs created for everything? You know, how is it that you handle multiple claims across multiple documents, for instance?
So we basically convert to the graphs, we convert the independent claims, we convert the whole claim sets, and we convert the whole specifications with the claims and specifications. But when we train the AI, we use mainly the independent claims and full specifications and millions of these pairs, like good pairs of prior art, and then also negative, bad pairs of prior art, so that it learns to draw the line between relevant. And why we use the independent claims is that we want that very short input would suffice in IP Rally to find the novelty killing prior art. And usually the independent claim is the shortest definition for the invention. And that also becomes quite clear in the demo when we jump into that how
Okay.
short input suffices. Yep. Did you froze? Oh, you are alive.
No. Yeah. Okay. Let's go on. So yes, back to the metrics. So as mentioned in the previous slide, the main metric we use is the examine expectations, and we use top n recall, where n is then can be different values from 5 up to 100. And the metrics figures here are from obviously the metrics are very sensitive to what kind of data set we use. So these metrics here are citations from and to EPWO US documents, and only for examiner labeled novelty restoring documents, so XOR 102. And here we use simple family deduplication for the target search result set. And these values here, so 18% top 10 recall and 33% top 50 recall is for a so-called invalidation search. So then we use for searching the full specification of the document that we are interested in. But as Sakari mentioned, you often obviously the search what you're actually searching with is much smaller, and you can also search with a much smaller text and still get very similar results. For instance, if you search with the full claim set, then the results are almost the same. The top 10 recall is 60% and the top 50 is 30%. So you can have quite a small text and still get very good results. And here we now you see a few quotes on the right. So several patent offices use our tool, and when they actually use it, they find more relevant documents than these metrics would tell you, precisely because of the reason that if an examiner would have seen the documents that the search engine produces, he or she might well have cited them. So actually, this metric is far from perfect, because there are probably other documents that are very relevant, even though they weren't originally cited. Yes, and then to the qubit dataset classification task. So we have the qubit dataset is a binary classification task of just there's a list of documents, and they either belong to the are of the qubit type or not. And how we approach this classification is that we have, as mentioned previously, we have pre-processed all the patent documents into graphs and then into vectors, and we just take these vectors and no other information. We don't use for instance, the patent classes or the applicant info or anything, just the vectors created from the text of the patent. And we train a simple logistic regression classifier on these vectors. So the training, depending on the amount of samples we use, takes a few seconds or up to a minute or two. And Then if you want to classify documents, it's basically instant. You give it and then you get the result. Is it for the class true or false? And because the search engine has so much information learned from when it has trained for the prior art task, we can with very few samples get a good classifier. So already with 10 samples, we can get an F1 score of 0.7 on average. This of course depends a lot on which samples happen to be chosen from the dataset, but on average we get 0.7, and on 75 samples we get 0.86, and from there it only improves slightly to about 0.9 when we add up to 500 or 600 documents. So with very small, you don't need to have many documents labeled to get already quite a good classifier, because the engine already knows so much.
Yeah. That is one thing that struck to our eye when we did this classification task, thanks to Tony's initiative, that actually it seems to have as a side effect, the AI model seems to have pretty good understanding of technology, and then it's easy to build classifiers on top of that.
Yeah, that's really interesting, because as you've mentioned, your tool is focused on prior art, patentability, a lot of detail. So not a broad classification into sort of big buckets, as it were, qubit, not qubit, quantum chemistry or quantum computing, and so on. So the fact that you're able to get this sort of result, 0.86, is very reasonable, very, very reasonable, right up there with some of the other systems we've seen that are actually optimized for a classification task. So that's very good. Yeah, looks great.
Yeah. Then we also
great. Then we still have the yeah. So the other metrics that we have been thinking of that we could use in a larger scale is that even though the examiner citations per se can be problematic because of the documents that have not been cited, even though they could have been, if we use only the data, if you think of what one examiner has cited as novelty drawings or X, or just a very close related document A, and compare these two and see how they are ranked in the search engine, then we get somehow perhaps a more reliable metric, because then we know that the examiner has actually seen both these documents and has given them an internal ranking in the sense that one of them is a novelty destroying document and the other one isn't. So this metric, that we call X versus A citation ranking, is that we look at documents cited by the same examiner and see how often the X citation is above the A citation in the search result list. This is obviously a very hard task because of the A citations are very closely related to the document, but still that also makes it a good metric in the sense that if this can be solved, then we know that the search engine is extremely good. And with our the previous generation of our model, we now get to 59%. So in 59% of the cases, the X citation is ranked higher than the A citation. So far from perfect, but it still gives indication that the model finds more often, at least, the X citations more relevant than the A citations.
Yeah. Everyone who has worked in this field knows how into details you are when you are making the difference between X and A citation, and if machine learns that well, then it's super good. Yeah. Okay, I think the audience deserves now a small demo of the platform, now that we have been talking so much about it. And I thought, unless there are some questions at this point.
There are, and one in particular that I think I'd rather save it until we get to past the demo, because we are coming up on 50 minutes in, and we want to get this demo and give you an opportunity to show that the nuts and bolts about exactly how it works in practice. So I'm going to hold on to these final couple of questions. And please, if you've got additional questions, go ahead and put them in now, because then we'll go ahead and start addressing those after the demo.
Yep. Okay, this is the IP-Rally landing screen. Basically, the search needs to be in the graph format, but you have several ways of building the graph. You can use like a notepad style editor to build the graph. I can show that. You can start the search with publication number. That's in the sweet spot of IP-Rally, because then you have the claims, you have in the description available, and it's super handy for invalid searches. It's also like state-of-the-art searches around a particular patent. Or then you can just copy paste the claim, an abstract, the full claim set, or any invention disclosure into the full text box, and then the graph conversion will be done automatically. But just to show like a very brief demo with a very short input, we mentioned that that's one of the benefits of IP-Rally, that a short input gives you good results. So if you define an ordinary seat, most of the audience is sitting on some kind of a seat currently, and we want to find seats having a seat portion and backrest. Let's define that as the graph. And well, obviously you get all kinds of seats. This is also a seat, kind of a seat, Chinese document. We get a joyful chair. Okay, we seem to be on the topic. Okay, let's define a little bit more. We want to find a fancy seat that has a ventilation system, which has some air channels. So a little bit more comfortable seat. Then you just add them using the graph formula. Seat portion having a ventilation system, having air channels. And I just type them in and hit the search button again and see how it's reflected in the results. The first hit is an ordinary office chair, but it has a ventilation system here. Okay, novelty destroying prior art. Automobile seat with ventilation device. Yes, another ventilated automobile seat, another seat with ventilation. Summer cool seat. This is my favorite in this results. Ventilated summer cool seat. Okay, now I realized that, okay, I'm not into those summer cool seats, but I'm into vehicle seats. So let's tell the AI. It cannot read your mind, but when you tell it that you are interested in vehicle seats, then something may happen. Just with one word, you get rid of the cool chairs and office chairs, and now it's a vehicle seat which is ventilated. The next hit also vehicle seat having air channels and being ventilated. Also the next one, and so on. So clearly, even a small change in the input gets you to the right direction. Okay, you see a lot of ventilated seats, but you don't see much control electronics in these figures. But if you are not interested in ordinary ventilated seats, but some that have some control system there. So let's type that in. The vehicle seat has a control system, and the purpose for that is for controlling airflow in air channels. And now you see that we are starting to build like connected info into the graphs. There are a lot of connected info already there, but now we are telling a more complex the function of the control system, what it actually does there. So I'm using a previously defined term there. Okay, let's see how it's reflected in the results. Now the first hit is a seat with ventilation system, and you clearly see that there is some control electronics here. The next hit also, it's a ventilated seat having control electronics. Clearly the results are going in the right direction. Also the next, and so on. You don't see not so much of these non-controlled images anymore there. And okay, now I'm just looking at the images, but the real power here is that IP-Rally also does you the content analysis of the documents. So now I'm opening hit number 6 here, and you see some highlights here. the seat bottom blower unit, draw airflow into seat bottom. So you see that, okay, now this there's some air flow related stuff here. The AI highlights it with yellow color. It thinks it's relevant to you. And here there is a controller and independently control the blower unit and the back blower unit. Okay, there's this control system also, and the AI finds it from the document, even though it uses different terminology to some extent. And how this is possible is that because there is this underlying big full specification graph behind this document. So now you can see here the graph. For transparency reasons, we publish these graphs also for the users, so they can see that what is the content that the AI actually sees. And they are really long, full of technical details. All the connections are identified. And if there are patent attorneys who have taken the EQE exam, I sometimes call this like an EQE paper C machine. So if you want to see that which are the features that match, how would I do my opposition case, for example, in this case, I need to find the matching features. You can move the slider here and ask the AI to throw away the irrelevant features. So only the matching features will remain here. And now we see that when I turn the slider right, the number of features reduces, and when I get to this level, then there is still a little bit too much. I take still a little bit too much. So now I see that there are only these ventilation system and blower and also independent blower control. So only pretty relevant features left in this graph. And basically the yellow highlights are converting these reduced relevant graphs back to the original text to show where the signal comes from.
Yeah, well, there's absolutely no way anybody could call this a black box. I mean, this is fascinating. I mean, honestly, I mean, you can't ask for anything more explicit, and the ability to pretty quickly judge and adjust the sensitivity. So this is very impressive, very impressive. Do you have a couple other things for the demo? I mean, we're coming up on 55 minutes. Almost everybody has stayed on, so that's fantastic. And so let's look at one or two things quickly, and then there are a couple of questions we can get to before the top of the hour.
Yeah. I could probably do, now that there was this question about chemistry, I could do like an invalidity search for a chemical case, just typing in the publication number here. It's a phenyl and ether oligomer composition, and now I get to choose if I use the full specification as the starting point or if I make a targeted search for a particular claim. And now I choose claim 1 here, and the magic happens when I press the blue button. It's converted in the graph format. Now you see how the machine understood the claim, how it understood the technical details. You see that the ranges are picked there. The AI has that information in well-structured format, and you get the results in a similar way than in a mechanical case. And how you could do is you can do the analysis using this highlights. You can go through the result list in short format or using the image mosaics. You can flag the best hits here with the heart symbol, and then you can ask the AI to use that information to improve the search. We call that zoom to favorites. And now when I use that one, then the AI pays more attention to those features that are common in this original query graph and the two flagged references there.
Yeah, that's really fascinating. Traditionally, of course, chemical patent searchers are so focused on structures, and rightfully so. But more and more of these types of patents, to avoid an emphasis on structure searching, you get the properties of the material and ranges of properties of the materials. And this seems to be doing a really good job of identifying those items and putting them into the graph. So I think that's actually really fascinating. Is there anything else you want to show quickly, or should we go into a few questions before we wrap up?
I think we could move to the questions. If you use the free text search, that it's basically the same thing that it just uses your free text input. But
yeah, so it's really simple to create graphs. You can either create them yourselves on the fly, adding elements as you go to narrow your result set. You can use a sample document as an example, or you can paste in some free text from an invention disclosure, for instance, and that's going to generate your graph, which you can tweak based on what it is that you think should be part of the query.
Yeah, just showing that the snow cycle appears in the results when I use the man-powered vehicle graph, which I used as built from the free text. Yeah, we can go to the questions.
Yeah. Okay. So I'm going to ask this. The most recent one first. How does your system deal with features that are interconnected? For example, if the control system is defined as a feature for controlling both the airflow and also another system, such as a movement system, how would the system deal with that from a graph perspective if the control system, for instance, has multiple control functions?
Basically, what I would do, I would just add both those functions. So every feature can have several functions, and I would just like I typed that for controlling the airflow, I would add another feature for controlling the movement of this and that. And then the AI has that information, and it can use that in the search.
Yeah, it seemed like the graph that you showed us at its highest level, with the highest amount of detail, had those redundancies built into it. So it seems like if that's built into the graphs that are being created for the documents in the collection, then yes, if you build something similar where it's interconnected in that sense, it should still work really well. Okay, so let me let's see, a couple more here. Now, there was a question here about document level search similarity. I'm not entirely sure what that means. So if the person who wrote that can maybe provide a little bit more detail about what they mean by that. Another one, back to the X versus A. I don't want to spend a lot of time on this because, I mean, theoretically, an A document can be even more relevant than an X document. It just happens to have been published after the date where patentability is subject to. So the fact that you've got a number around 50% is actually exactly what I would expect. I think there's probably just as many A documents that are more relevant, but they're not novelty destroying because, of course, they've been published after the application date, and therefore you can't use it. So there was a question about that. I didn't just want to leave it out there, but I think it's pretty easily addressed. So another one here. It seems as if you can work at a variety of different levels also as far as, I mean, the exact question was, in USPTO practice, examiner is required to search before the first action all claims, independent and dependent, to be ready to claim amendment. They also advise to search unclaimed matter, which can be added later to avoid additional searches after update applies. Similarly, IP Rally, while focusing on independent claims, could repeat searches for dependent claims as well. It seems like the graphs that you showed also did demonstrate a full accompaniment of all the claims, not just the independent ones. And so finding something within a dependent claim should be no issue.
Yeah, you just add the dependent claims to the input. The algorithm takes then all the features into account that are in the independent plus dependent claims and make the search based on that. And it's as simple as that.
Okay, so I've gotten some clarification on that other question. Then we're going to go ahead and wrap things up. There are a few additional questions, but those will be part of the results that I'll send you from the registration report. How is it that the system decides the relevancy ranking? the way it was asked, given patent P, find the 10 most similar patents. So your system does have a ranking as to how are the results displayed to the user. Can you address a little bit about how that's done?
Basically, it all comes back to the vector comparison in the end. So we play with numbers, and basically the relevance ranking is the way the currently trained AI model sees to technical relevance, the highest ranking on top. The scores that you saw, you shouldn't pay too much attention to the absolute value, but maybe the relative value between documents. That's more important in our model.
Yeah, relative distance is generally a much better comparison, because of course it's relevant compared to what? There's always got to be some context. And so, okay, well, again, there was a couple more questions. I'll leave those to be addressed offline. Gentlemen, thank you ever so much. Fantastic session, fascinating approach to tackling this particular problem. Lots of transparency. Thank you for all the detail. And again, can't thank you enough for being here with us today, the audience. For those of you who came and attended live, thank you so much. Again, the handouts are there before we close this down. Grab the handouts if you haven't already, and look for a link to the recording to be sent via email tomorrow. And once again, thank you everyone, and have a great rest of the week.
Exactly. Thank you, Tony. Thank you, everyone.
Thank you.
See you.